So hello everyone. Today we have Pushpita Das, who is doing her PhD thesis in the University of Amsterdam, and she will be presenting her work on the GRMHD simulations of accreting neutron stars. Go ahead.
Yeah, thanks. Thanks a lot. Thanks for inviting me to give this talk. So I'm currently a PhD student working with Oliver Porth and Anna Watts on GRMHD simulations of accreting neutron stars. So my work mainly focuses on extra binaries. So extra binaries are basically two-body systems where you have a donor star, and then you have a compact object. So the donor star eventually fills up its Roche lobe, and then you have mass transfer through Roche lobe overflow, and then you have a disk around the compact object. Now, at the center of the accretion disk, there can be either black holes or neutron stars. So in this talk, I'll be mainly focusing on neutron star extra binaries, which basically means that you have a neutron star in the middle of the accretion disk. So why are the systems interesting? One of the reasons behind studying this is that they can help us understand neutron star equational state. Now, dense matter equational state maps directly to the mass and radius of the star via the stellar structure equations. One of the ways to, if you can measure out the mass and radius for a lot of neutron star sources, you can better constrain neutron star equational state. Now, one of the ways to do this constraining mass and radius of neutron stars is via pulse profile modeling. So this pulse profile modeling technique actually exploits the fact that the emission from the surface of neutron stars are modulated due to general relativistic effects. So in the movie here, on the left, you see the brightness as a function of time as the neutron star rotates in presence of no gravity. And in the right, you basically see the modulation in the emission that you see from neutron stars in presence of strong gravity. So let's get into a bit more details on how the pulse profile modeling technique actually works. So you have your data, which is basically the photon counts as a function of rotational phase of the neutron star. And then you have your instrument response matrix that you like for the telescope. And then you have your light curve model, which is basically a theoretical model. So using the best of the theoretical knowledge that you have, you construct a star, and then you construct the regions from where the star is emitting. And by doing general relativistic ray tracing, you form synthetic pulse profile from your theoretical model. So you have your synthetic energy as a function of rotational phase of the neutron star, and then you have your actual data, which is basically also energy as a function of rotational phase of the star. And you feed all of these three components into a Bayesian inference code. And then by doing a likelihood calculation, you basically get out the mass and radius of the neutron star. So this is a pretty well-established technique, and NICER has been exploiting this, or NICER has been employing this technique, and we basically have the measurements for two different neutron star sources. So NICER has been looking, until now at least, NICER mainly has been looking into rotational powered millisecond pulsars, and we now have the measurements for two of the sources. Now, along with providing pretty tight mass and radius constraint, NICER also pointed towards the presence of multipolar surface field on top of the this rotation powered millisecond pulsars. This actually branches off to give rise to a different set of questions, like how do you make those multipolar surface fields in neutron stars, which I'll come back to in a bit. So apart from the isolated millisecond pulsars, the other sources for which you can do mass and radius inference for neutron stars using pulse profile modeling are accretion-powered millisecond pulsars and thermonuclear burst oscillation sources. So both of these, in both of the cases, you basically have the neutron star rotating, like you have a really highly rotating neutron star, like with a millisecond time period, which is why you have a much stronger like you basically can see the GR effects much more prominently in the pulse profiles that you get from these sources. So right now, though the telescope, like right now, though there has been only this inference for isolated pulsars, but the future telescope would also be looking into accretion-powered millisecond sources. So these are interesting in terms of like mass and radius of neutron stars. So that's one aspect. The other aspect is these are neutron star X-ray binaries are really good candidates to study neutron star jets. Now, you see jets in both black holes and neutron stars. Now, though there has been really a lot of study, both theoretically and from an observational point of view on black hole jet formation, there has not been much studies on neutron star jet formation. So currently there are two main classes of theories. One is the Blandford-Znajek mechanism, where you have a centrally rotating black hole or ghost sphere twisting up the magnetic field and launching jets. And the second class of theories, mostly known theories, where you have a Blandford pane mechanism, where you have the accretion disk tangling up the magnetic field and launching jets. Now, one of the main differences between black holes and neutron star in the context of jet formation is that neutron stars have a solid surface and they have their own magnetic fields anchored to the surface of the star. And in case of neutron stars, unlike black holes, you can basically measure out the spin of the neutron star and also the magnetic field of the neutron star pretty clearly, or pretty much clearly. So you can basically tangle out, by studying these systems, you can tangle out, like you can basically figure out the effect of the spin and the magnetic field on the jet power. So this can actually maybe help us to go a step further in understanding how these relativistic jets are actually formed. So GRMHD simulations can help in understanding these neutron star jets. And in terms of this pulse profile modeling, a lot of things are currently unknown in the surface emission models of these accreting millisecond pulsars. For example, we don't know how the hotspot shapes look like. We don't know if the hotspot shapes move. We don't know if there are accretion variability on top of these hotspots. And we also don't know if like how all these factors come into play and how these are going to be impacting the emission that you see at the from these sources. So we started doing this mainly into with 2D in spherical coordinates. So we basically use the black hole accretion code, which is Bach, and then this is basically the numerical setup. So the plot you see here is a log of density plot, where the red basically means it's a highly dense region and the blue means it's a low density region. So we set the stellar magnetic field, which is here, at the surface of the neutron star. And then we also have a torus, which is basically this. And we set the torus magnetic field always in our system such that they are anti-parallel to the stellar magnetic field. And the implications of this, I'll come back to it in a bit. So neutron stars mainly have really high the surroundings of the neutron star have a really high magnetization. Maybe you have most of the time you have sigma of, just to maybe quote a number, of sigma of 10,000. Of course, we cannot do a sigma of 10,000 with our current codes. The best we can do in MHD currently, at least, is going to maybe a sigma of 100, that too with a lot of tricks coming into play. So in order to maintain this highly magnetically dominated region close to the neutron star, what we do is that we drive the solution inside the light cylinder radius to some target pressure and density values, such that the sigma is always set to 100 and the plasma beta is always set to 10 to the minus 2. And once the accretion fluid starts coming in, we basically modify the solution. So what we do here is that we initialize a tracer. So the disk is having a tracer value of 1, and then you have all the other region where you have a tracer value of 0. And then as the disk starts coming inside the light cylinder radius, we add the solution depending on the weights of the tracer. Now, once the accretion flow reaches the surface of the neutron star, we set a continuous boundary at the surface of the star. That is, we allow the matter to pass through unhindered. So you basically have a continuous boundary conditions for pressure, density, and also the parallel velocity component. And as for the magnetic field, we separate out the neutron star wind region from the accretion column and the closed zone, and then we fix p theta component at the stellar surface, and then we extrapolate b phi as r to the -2 in the wind and put b phi to 0 in the closed zone. So as a first case, we did the dipolar magnetic fields. So here, the different panels are showing you the cases for different stellar magnetic field strength here. So the lowest one is basically this one. The middle one is an intermediate magnetic field strength, and this one is basically a really high magnetic field strength. And the green box here is just showing you the initial star disk field configuration that we start off with, which is antiparallel in this case. Now, as I start evolving the system, for the lowest magnetic field strength, you have the disk crushing the magnetosphere, leading to a boundary layer regime. As you go higher up in the stellar magnetic field strength, you have the magnetic pressure of the neutron star stopping the disk, like somewhere further out from the stellar surface, and then you end up in a channeled accretion regime. And then as you increase the stellar magnetic field strength further up, the neutron star magnetosphere doesn't really allow the disk to come in and accrete, and then you basically end up in a propeller regime where you have the neutron star magnetosphere preventing the accretion flow to reach the stellar surface. Now, propeller in our case doesn't really mean that the system is not accreting at all, but rather it basically means that you have a lot of ground pressure that builds up. So you have a lot of ground pressure that builds up at the inner disk region, and then at some point where the ground pressure is like really high, you basically have burst of accretion that makes its way through at the surface of the star. So we do get different accretion states depending on the stellar field strength of the star. And this was also done by Paffray and Tchaikovskoy in 2017. And then since we are interested in how the hotspots of accreting sources look like, these are all 2D. We don't really have a spot. What we have are basically rings, because these are all axisymmetric. So what I show here is the temperature profiles as a function of theta, where theta goes from 0 to pi from here to here. So what we do is that we take all the mass flux that reaches the stellar surface, and then assuming that it's emitting as a black body, we convert that to temperature. Now, the different colors here are showing you the columns, like the column shape for the different stellar magnetic field strength. So the blue line is just showing the lowest magnetic field strength, where you have a boundary layer regime, which is why you basically see the star glowing all over the place. Now, for the rest of the cases where you do have a channeled accretion regime, we can try to understand the position of these columns qualitatively. So let's call this angle theta max 1. So this angle basically depends on the magnetospheric radius. Now, the magnetospheric radius is basically the radius at which the magnetic pressure of the stellar magnetic pressure becomes equal to the ground pressure of the disk. So as you go higher up in the stellar magnetic field strength, the dipolar stellar magnetic field strength, you basically push this magnetospheric radius further outwards. So you have matter latching onto field lines that are more and more closer towards the pole. Now, let's focus on the other angle. Let's call this theta min 1. Now, this angle, if you look at the system from the equator, this theta min 1 angle is basically the field line, the field line that is attached to the disk, like the last closed field line, the last connected field line to the disk, and it's mainly a disk property. So as you go higher up in the magnetic field strength, you push this radius further outwards and move this angle more and more closer towards the pole, but you're not really changing this theta mean 1 angle. As a result of this, you get more thinner and thinner columns as you go higher up in the magnetic field strength, and you also like move the columns more towards the pole as you go higher up in the dipolar magnetic field strength. Now, as I was mentioning before, that NICER actually came up with field structures that are not really dipolar in any ways. This actually brings us to a couple of questions. So the rotation-powered millisecond pulsars are assumed to have gone through a prolonged accreting phase before reaching that stage of their life cycle. So now the question is, was this accretion that somehow modified the field and gave rise to this multipolar stellar field topology? Or were these field structures present even during the accreting phase? And if they were present, how did the accretion flow on top of this, on top of this multipolar field structures look like? Is it somehow related to why we only see around 20 accreting millisecond pulsars amongst almost 130 known low mass X-ray binaries? Is it because in most of them you have this multipolar field structures and then you don't really see pulsations from them due to this? And also, what happens to torques in the system? So in order to actually explore this a little bit, we did a couple of simulations with the quadrupolar fields. And also we did a couple of simulations where we played around with the dipolar and quadrupolar fraction at the stellar surface. So here again, what you see are different magnetic field strength, but now for quadrupole. So here you have the lowest quadrupolar field strength, here you have an intermediate, and here is the highest quadrupolar field strength. And this is again log of density. So for the lowest quadrupolar field strength, you do end up with a boundary layer again. But now the boundary layer is kind of asymmetric in the sense it is like shifted upwards. And then as you go further up in the stellar magnetic field strength, you end up with two accretion columns, but now one is at the equator and other is more closer towards the pole. And then as you go higher up, you basically have a really strong equatorial hotspot and a much weaker polar hotspot. Now, why is this asymmetric behavior happening? So if you go back to the initial stages, so what is happening here is that you have a disk magnetic field, which is anti-parallel to the stellar magnetic field in the upper hemisphere, and you have a disk magnetic field, which is parallel to the stellar magnetic field in the lower hemisphere. So as a result of this anti-parallel and parallel configuration in both the hemispheres, it's really easy for the disk to reconnect with the stellar field through the upper hemisphere, and hence it actually proceeds, the accreting flow actually proceeds via reconnecting with the upper hemisphere, and then as a result of this, you see this asymmetric behavior. So how does the surface temperature profiles look in the system? So what you see here again is a temperature, temperature distribution as a function of theta at the stellar surface. So as you increase the quadrupolar field strength further up, what happens here is that the equatorial column becomes more and more narrower, and then the polar column is basically moved more closer towards the pole. Now this column can actually be either in this hemisphere, or basically this thing can also flip depending on the disk magnetic field that you put in. And then we actually played around a bit with the with different effective dipolar and quadrupolar field strength in the same star. So to plot a reference point, the blue curve here is basically a pure quadrupole, and then we start increasing the dipolar fraction in the star. Now, while we increase the dipolar fraction, we basically also decrease the quadrupolar fraction in order to keep the total magnetic field of the star to be the same. Now, as you go higher up in the dipolar fraction, what it does to this column is that it moves the column further closer towards the pole, and along with this, it also makes the column much more broader with an increase in dipolar fraction. All right, so the systems are also quite variable. So we do see a variability in this hotspot at a scale of 10 milliseconds. So the different colors here are just showing you the 10 millisecond averages for like different 10 millisecond averages. And the black dash line is just showing you the average temperature over the whole simulation timescale. From, let's say, from 20,400 to 28,800. So yeah, the systems are quite variable, but this is just the variability in the mass accretion rate, and or because due to the column moving a little bit from where it is on average. But whether this variability is translated into the emitted spectrum, that's a different question, and that needs a bit more of a thought, which we were going to do in future. So apart from the hotspots that we were interested in, there were a couple of other interesting things that came out of the simulations. So we wanted to look into the star-disk interactions. Before I go into how the torques behave in the system, we need to know a couple of names, let's say. So first is the magnetospheric radius, which is the inner disk radius, which is decided by the equilibrium point between the stellar magnetic field and the round pressure, magnetic pressure of the star and the round pressure of the disk. And then you have the co-rotation radius, which is the radius at which so co-rotation radius basically is the radius at which the disk rotates at an angular frequency which is equal to that of the star, which basically means that if you're sitting on the star, the region inside the co-rotation radius will basically rotate at a speed which is larger than the angular frequency of the star. So the region inside the co-rotation radius will exert a spin-up torque, and then the region outside of the co-rotation radius will basically rotate at a speed which is lower than the star and hence exert a spin-down torque to the star. And then there is the light cylinder radius, which is the radius beyond which the stellar magnetic field lines have to open up so that they don't rotate at a speed which is larger than the speed of light. So if you have magnetic field lines, if you have the stellar magnetic field lines connected to the disk, and if the stellar magnetic field lines are connected to the disk, which is inside the co-rotation radius, means that the foot points of these field lines are basically rotating at a speed which is larger than the stellar frequency, and hence these field lines will basically exert a spin-up torque to the star. And if they are connected outside of the co-rotation radius, they'll exert a spin-down torque. Now we looked into how the torque behaves as a function of time in a dipolar case. So this is basically the case where you have this equation scenario on an average. So you have the magnetospheric radius, which is inside the co-rotation radius, and you have a nicely channeled accretion regime. Now, the whole plot actually looks pretty crowded, but let's try to get through this one by one. So here, every time when I talk about positive, it means that it's spinning down the star. And when I talk about negative, it basically means it's spinning off the star. This is some convention that we just go with in here. So we divide the total torque into the electromagnetic torque and the matter torque. So the matter torque is, since the magnetospheric radius is inside the co-rotation radius, matter torque is always spinning up the star no matter what. And this matter torque just contributes to almost like 1% of the total torque. And this is all in agreement with what people found before me as well. So now the most of the spin down torque, the total torque, is always spin down in this case. And the most of the spin down is basically coming from the electromagnetic fields. Now the question is, why is that? Ideally, from a theoretical point of view, what do you expect in the nicely channeled accretion regime with a magnetospheric radius smaller than the co-rotation radius is that it'll be you will spin up the star. But this is not really happening here. So in order to understand that, we divided the electromagnetic torque further into the wind torque and the disconnected torque. So what is wind? So we basically single out all the field lines that are open. So here the dashed line is just showing you the light cylinder radius, and all the orange field lines are tagged as open in this case. And all these field lines contribute to the wind torque in our case. And all the other field lines, namely the accretion column and the field lines that are still connected to the disk, contribute to the disconnected torque, which is the one shown in red here. So two things. So the disconnected torque is almost equal, if not more than the wind torque. And then the disconnected torque is also it's contributing mostly to the spin down torque that we see here. Now, why is this? Is this because you have a lot of field lines which are connected to the disk beyond the co-rotation radius? Meaning, do you have an extended magnetosphere? We don't know. And in order to get a bit more info on this, we basically looked into the angular momentum transport in the disk. Now, before I go into the total angular momentum transport in the disk, we also looked into how the torques look like in non-dipolar fields. So here again, you see the averaged torque at the stellar surface in y-axis, and in x-axis, you see the quadrupolar fraction. So Q0 basically means it's a pure dipole, and the last point in the Q here is the maximum Q here basically means it's a pure quadrupole. And all the points in between are basically where you have some dipolar fraction and some quadrupolar fraction. And we played around with both of them, but kept the total stellar magnetic field to be the same. Now, as you go higher up in Q, you decrease the spin down torque. This is because of two things. First, as you make the field structure more and more quadrupolar, you basically make the wind much more weaker. And also, what you do is you push the magnetospheric radius further in, closer towards the star. And as a result of this, you also decrease the spin down torque that you get from the electromagnetic fields, like the disconnected fields. And then you also have the matter torque, which kind of increases as you go, as you increase the quadrupolar fraction. Now, getting back to the point of why do we always see a spin down, even though you're expected to see a spin up from a theoretical point of view? So we looked into how the angular momentum transport in the disk actually looks like. So the upper panel here is just showing you so the lower panel is showing you the mass accretion rate as a function of radius, and it's pretty much constant, which basically means that the disk is in a quasi-stationary state, at least until in the regions that we care about. And in order to understand the stress, like all the stresses, what we do is we take the TR phi component, and then we decompose the TR phi components into an average and an instantaneous component. And these are all the terms that we come up with. There are a lot of terms, but there are only a couple that are most interesting. So we tried to see how all these terms behave as a function of radius. And it is really hard to say anything about this plot, like anything about the angular momentum transport from this plot. So we tried to look into how the total angular momentum looks like in a 2D space in the disk. So here, red basically means you're transporting angular momentum outwards, and blue means you're transporting angular momentum inwards. So panel A is showing you the angular momentum transport due to mean magnetic fields, which basically means due to large-scale magnetic fields. So you basically have a really high outward angular momentum transport in the jet, and then you have almost none in the disk. In the disk, this angular momentum transport is immediately taken over by Maxwell stresses, and it's mostly transporting angular momentum outwards. Now, as I was saying before, we were suspecting that there might be an extended magnetosphere, meaning there might be a lot of field lines that are connected to the disk. But looking at this plot, it doesn't seem to be the case, because if there were an extended magnetosphere, you would have mean magnetic field stresses would not have dropped that rapidly. You would have seen a lot of magnetic stresses as you go outwards in the disk as well. So it's not the magnetic fields that is probably making all the difference here. There is something else that's coming that is in play. Now, since we were looking into this, while we were trying to make sense of all this, one really interesting thing that came out of this is that the whole thing, like, okay, so before I go into this, this panel, it's basically showing you the mean velocity field stresses, where you have inward angular momentum transport in the disk and in the columns, which is expected. So you basically transport angular momentum inwards through the disk and in the column. And then you have an outward angular momentum transport in the winds. But the term that was most surprising was this term. This is basically a correlation between the radial velocity and enthalpy. And we don't know what actually causes this. We have a kind of a explanation for this, that it might be happening because in most of the cases that we see, at least in the movies, that we see that you have a larger blob, which is basically means you have larger density blob, which is making its way through at the surface. You have a larger blob, which is falling onto the surface of the neutron star. And then you have a smaller blob, which is flowing outwards. So maybe this is actually causing this really high correlation between enthalpy and radial velocity. So we don't know. Might be a 2D effect as well, and we will not know this until we actually look into the whole thing in 3D simulations. So the extended magnetosphere that we thought was the case for the spin-down in most of our cases were not true. So why is this? So we then looked into how the angular frequency looks like as a function of radius in the equatorial plane of our simulation. So the different colors here are showing you the angular frequency as a function of radius for different stellar rotation, stellar angular frequency. And the black dashed line is just showing you the Kepler frequency. So our disks are mostly subcaplarian in the inner parts, in the inner magnetospheric parts. So they are nicely Keplerian at the outer like at an outer radius, but as you go close to the neutron star, you basically have a subcaplarian disk. So what it does is, due to the subcaplarian disk, you basically move the corrotation radius further closer towards the stellar surface. And then you're basically in a spin-down regime, as you'd expect from a theoretical point of view. So why? So we kind of have some explanation for why these disks are subcaplarian. Maybe it's so this subcaplarian behavior actually happens when you have an Alfvén speed, which is kind of close to the sound speed. So maybe it's the magnetosphere which makes it the subcaplarian somehow. But this actually solves why we do see a spin down, which is great. So can you also get jets from neutron stars? Yes, we do see jets in our simulations. So the color that you see here are log of magnetization, and the panels are basically showing you a dipolar case in this one and a quadrupolar case in this one. In both the cases, we do see jets. Now, we define jets as the sigma 1 contour, which is shown by the white lines here, by the white line here. Now, what we find after a couple of runs is that it's the disk that makes a huge difference in how much jet power you're going to get. It's the disk magnetic field that actually decides how much jet power you're going to get at a quasi-stationary state. So this is how the jet power looks like as a function of angular frequency of the star and the stellar magnetic field strength of the star. So the green line dot here is showing you the output from the simulations, and the solid red line is showing you the isolated power scaling. So initially, you do see an enhanced jet power compared to the isolated power that you'd see in a neutron star. But as you go higher up in the stellar, like in the angular frequency of the star, you basically see that suddenly you're getting less power compared to an isolated state. And similarly, this happens in as you try to play around with the stellar magnetic field strength as well. So initially you get an enhanced jet power compared to the isolated neutron star scaling for lower magnetic field strength. But as you go higher up in stellar magnetic field strength, you basically get lower jet power, lower jet powers compared to the isolated scaling. And this is all because of the disk. So, okay, so I'll come back to why this is happening in a bit. Before I go there, just to give you an idea of what we are talking about here, if we convert our simulation to CGS units, if you have a mu of 30, and mu 30 corresponds to 10 to the 9 Gauss, you basically have a jet power of 1.7 times 10 to the 35 ergs per second. And this is basically the Poynting flux that we're talking about, in the jet power. So why do we sometimes see an enhanced jet power and sometimes see a lower jet power compared to the isolated scaling? So this all happens because of the flux opening or flux closing due to the accretion disk. So what happens is that you have a star and you have a disk, and as you start rotating the star actually launches an Alfvén wave, and then you have flux bundles from the Alfvén wave that gets trapped in front of the disk, at least in our case. Now, depending on how fast the star is rotating or how strong the stellar magnetic field strength is, you can either have the disk field being antiparallel to the flux bundle from the Alfvén wave, reconnect, and basically give rise to an enhanced jet power, or you can the disk can actually close down the normal open flux that we have, giving rise to a lower jet power compared to the isolated case. So the endpoint of this whole slide is basically that the disk can either close or open the initial closed. So the disk basically can either open this closed zone and leading to an enhanced jet power, leading to an enhanced open flux, or the disk can actually close this initially open stellar field lines, leading to a lower jet power in this accreting system. And this whole thing is actually dependent on what initial magnetic field strength that you start off with. And this actually says that it might be the jet power that you get at the end of this might be dependent on the history of the evolution of the system. Now, is this scenario still valid in a 3D case? Is the flux opening, how is the flux opening actually happening? So these are all 2D axisymmetric simulations. So how much of this can we trust? So we need 3D simulations. So these are basically preliminary simulations. So this is a simulation in spherical coordinates. So what you see here are log of density cuts, where this panel is just a cut in the ZX plane. And this panel is a cut in the XY plane, basically meaning the equatorial plane. And yeah, so as I start evolving the system, you have tongues developing in the equatorial plane. These are basically Rayleigh-Taylor instability in the equatorial plane. And then as a result of this, you have a really chaotic accretion in case of in the 3D case. Now, I haven't finished doing all the analysis yet. One of the things that we wanted to do is basically contrast the 2D and a 3D case and see how the flux opening actually occurs. This is still to be done. But what came in the middle is that in order to see pulsations from a pulsar, you cannot have an aligned case. You cannot have an aligned pulsar and still see pulsation. To actually see pulsations from this accreting millisecond pulsars, you need to have the magnetic axis, which is inclined to the rotation axis of the star. Now, as you try to start inclining the rotation axis, in spherical coordinates, what happens is that it becomes really hard to make the pole stable and make because of this really high magnetization that I need to maintain close to the neutron stars, it becomes really hard for the pole to handle all of this. So we actually went to Cartesian coordinates. So we do basically do our simulations in co-rotating Cartesian coordinates in spatial spacetime. Co-rotating Cartesian coordinates basically mean that the whole grid is basically moving with the star. So here again, we have a coupled force-free magnetosphere. So we still drive the solution to some target pressure and density and parallel velocity values. But now the sigma is a bit lower because it's really hard to keep these systems like without explosions at this high magnetization. So we go with a sigma of 70 and a plasma beta of 1.4 times 10 to the minus 2. And then at the stellar surface, as a boundary condition, what we do is that inside the star, the electric field is 0 because of the solid body rotation. So the magnetic field evolution actually follows from there. And the pressure, density, and the velocity of the star are basically set to some values at every iteration. So we always override the pressure, density, and the velocity components inside the stellar surface. So it's basically we are trying to mimic spherical boundary condition with in Cartesian coordinates. Right. So, and this works pretty well. So this is again, this is basically an inclined dipole. So now you have the magnetic axis of the disk, the magnetic axis of the star, which is inclined. And it's basically at a 60 degree with the rotation axis of the star. The star is rotating along Z and the magnetic axis is 60 degree from Z. So the plots that you see here, this panel is again a ZX plane, and this panel is in the equatorial plane. Now, as we start evolving the system, a couple of interesting things happen. So first, we do see MRI developing in the Cartesian coordinates, it's pretty nice to see. And then the accretion disk, what it does is basically it modifies the initial stellar magnetic field inclination that we start off with, and it kind of moves the whole thing. So it basically modifies the hotspot position that you would ideally expect. Right. So right now we are focusing on two things mainly. First, to see how the jet forms in this 3D simulation. So how the flux opening takes place in this 3D simulation. What role does the obliqueness play in all of this? And we are also focusing on getting some pulse profiles out of this. So depending on the rotation of the star, if you are in a propeller regime, depending on the opening angle of the jet, we sometimes do see striped jets. Basically means you have reconnection regions in the jet. And this can be pretty interesting in terms of like the emission that you get from the jets. So we are still exploring under which condition you would basically expect a striped jet. And we are trying to figure out how much of a role does obliqueness play in all of this. To give you an idea, and one of the interesting things that came out of this is that we try to check these are all in the early stages, but we try to check the jet power as a function of time in this simulation. And this is the orange line is showing you the jet power for the aligned case where you have the magnetic axis and the rotation axis to be the same. And the green line is showing you the case where you have a 60 degree inclination between the rotation and the magnetic axis. And from an isolated pulsar point of view, I guess you would expect like a jump in the open flux that you get as you start inclining the system. But we actually do get a completely different scenario where you have less jet power as you start inclining the system. So maybe you'll basically quench the jet when you have a 90 degree inclination. We don't know. This is the thing that's so we are still yet to run the case. And then we were trying to get some pulse profiles out of the GRMHD simulation. So we get these pulse profiles by doing a general relativistic ray tracing. So if you have a hotspot, which looks like this, so if the stellar surface look like this, so this is all normalized in terms of temperature, this is the pulse profile that you'd come up with. It has a really nice sinusoidal behavior, but the hotspot shape that gives rise to the sinusoidal behavior is kind of mad. So we still have to figure out what, this ray tracing is done without taking the accretion column and the disk into account. We need to figure out what effect does the accretion column, what effect does the accretion column play in all of this, and what are the important aspects that you need to take into account in order to properly do the mass and radius inference. What are the factors that you need to really take into account in order to get the information out of these pulse profiles properly. This is still on process, but yeah, we hope to complete this soon. So I don't really have much of conclusions to say right now from the 3D simulations, but these are the conclusions that we came up with in the 2D case at least. So with this, I'll just stop here.